Hey everyone, welcome back to another Permutations and Combinations video, yearly questions. Today we're going to talk about the 2016 exams. So first question from the February-March session. Hannah chooses 5 singers from 15 applicants to appear in a concert. She lists the 5 singers in the order in which they will perform. How many different lists can Hannah make? Now this is a very easy part over here. So we have 5 places and the order is important. So the first place 15 choices, then 14, 13, 12 and 11. So either you can take the product for these or you can just simply do 15p5. Both of these will give you the same answer. So 15p5 360 360. Right, easy. Of the 15 applicants, 10 are female, 5 are male. Find the number of lists in which the first performer is male, second is female, third is male, fourth is female, fifth is male. All right. So the order is important and these are different people. So 1, 2, 3, 4, 5. Sorry. So you have male, female, male, female, male. Right, that's what they said, male, female. Yeah, all right. So different possibilities for this. So you have 5 males. So 5 choices for the first one, 4 choices for the third one, 3 choices for the third one, sorry. And for the females, you start with 10 choices for the first one, 9 choices for the this. Alternatively, what you could do for males, you can do 5p3 because you out of 5 men you have to list 3 men, and for females you need to do 10p2. Both of these will multiplying these, so basically this would be 5p3 times by 10p2. This would be identical to this one. So whichever way you are more comfortable with, times by 10 p2. Oh, sorry, no, 10, 10, 10. So 54, 10 p2, 5400. Right. Hannah's friend Amy would like a group of 5 performers to include more males than females. The order in which they perform is no longer relevant. Find the number of different selections of 5 performers with more males than females. As you can see, the order is no longer relevant and it's a selection problem. So we are going to be using permutations. So we need more males. So males were 5, females were 10 in total. So we can have, since there is no condition that at least has to be 1 female, so we can have 5 males, 0 females, 4 males, 1 female, 3 males, 2 females, and if we continue with 2 and 2, they will become equal, and that's not what we want. We need more than that. So out of 5, 5c5, 10c0, 5c4, 10c1, and 5c3, 10c0. So we can just simply do that. So 5c5, 10c0, this is simply 1. 5c4, 10c1, 50. And 5c3, 10c, oh sorry, this is 10c2. Sorry, 10c2. So this is 10c2, 450. So 450 plus 50, this will add up to be 501. Right. Now, two of the applicants are Mr. and Mrs. Blake. Find the number of different selections that include Mr. and Mrs. Blake and also fulfill Amy's requirement. Right. Now, Mr. and Mrs. Blake, that means Blake and Blake, male, female, they have been selected. But for the three remaining places, again, we have multiple choices. We can have two males, one female, or we can have three males also. So remember, one male and one female were already selected. So out of 5, we are choosing 4C2 times by 9C1. And for this one, this would be 4C3, 9C0. Right, now we need to do that. 4C2 times by 9C1, 54. And 4C3, 9C0, 4. So total would be 54 ways. Sorry, 58, my bad. 58. And that's the February and March. Let's move on to May, June. Now let's see this question. Find how many numbers there are between 100 and 999 in which all 3 digits are different. Right. Since we're making numbers, so this is going to be order problem, the permutations. So as we can see over here, let's make the numbers over here. So between 100 to 200, then 300, then 400, 500, 600, 700, 800, and 900, and then the last one is 999. So how many places do we have? How many options do we have with the starting numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9. So all 3 digits different. So for example, if the first we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 choices for the first digit. For the second digit, we have 0 included also. All right, so we did not include zeros over here, but for second digit, we have zeros also. So 9 digits because 0 included in this choice, and then 8 choices remaining for the last one. You can also write it this way. So you can have 9 times by a 9, P2. This would give you the same answer. So 9 times by 9 times by 8. This is 648. Now, find how many numbers in part 1 are odd numbers greater than 700. So 7 greater than 700. So let's just focus our attention on this particular bracket. So we have like 1, 2, 3 possible places for these numbers to be. Like the number could start with a 7, it could start with an 8, or it could start with a 9. So that means there are 3 choices for starting numbers 7, 8, or 9. But for the remaining 2 numbers, since we need the odd number, odd numbers, right? So odd numbers can be 1, 3, the last digits of 1, 3, 5. If 7 is already there, 7 cannot be there again. So 9. If 8 is there, so 1, 3, 5, 7, 9 can be there. And if 9 is there, so that means 1, 3, 5, and 7 are there. So there are three choices, but all of these are different. So for this one, the first one, you have um, 4C1. No, sorry, four choices for the odd number. Then any other remaining number. So out of 10 digits, two have been taken, so 8 remaining. Similarly, for this one, you have 5 choices for the odd number at the end and 8 remaining in between. Same thing, 4 and 8. So 32, 40, 32. So 40 plus 64, that is 104. Right. Now, a bunch of flowers consists of a mixture of roses, tulips, and daffodils. Tom orders a bunch of 7 flowers from a shop to give to a friend. There must be at least 2 of each type of flower. Shop has 6 roses. So first, let's list down before we forget. So roses are 6, 5 tulips, 4 daffodils. Right. And at least 2 of each type. So they should be greater than 2. And what else was the condition? The total needs to be 7. All right. So total needs to be 7. So we can start with the lowest numbers first. Right. So what if we start with 2 roses, 2 tulips, and obviously we cannot have 2 anymore. So we would need 3, total 7. Then we can gently increase this number and reduce this. Then if we increase the number of roses to 3, you will have 2 tulips, 2 daffodils. And I think that's the only choices we can have, possibilities. Right. So 6 C2. Wait a second. Were they identical or different? Yeah, so all different from each other. So we can have this 5C2 and 4C3, 6C2, 5C3, 4C2. Then we have 6C3, 5C2, 4C2. So let's calculate them. So 6C2 times by 5C2 times by 4C3. This is 600. Right. And then we have 5C3, 4C2, 900. Then 6C3, 5C2, this is 1200. So 6 plus 9, 15, 15 plus, that will become 27. And that's about it. Right, okay, that was quick. All right, let's move on to the 6-2 variant. Okay, so let's see this. Find the number of different arrangements which can be made of all the 10 letters of the word wallflower if there are no restrictions. So if there are no restrictions for the wallflower, so wallflower. Now, as you can see, there are 3 L's and 2 W's. Right. If there are no restrictions, so that would be just simply 10 factorial for the total, 3 L's and 2 W's. So 10 factorial divided by 12, because 3 factorial is 12, 6, and then times by 2, 12. So 302, 400. There are exactly 6 letters between the 2 W's. Okay, so if we are putting a condition on 2 W's, that means we don't need to count them again, but we just need to at least take care of their placement. So 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So one possibility is that they are over here. So there are 6 letters, 1, 2, 3, 4, 5, 6. Then we can have it over here. And there's going to be one more possibility for placement, where the W's are arranged like this. So the rest of the letters, we only have to be concerned about these 3's. So the rest of it all is identical. So this would be 2 are already placed. So there will be 8 remaining, and with 3 L's, 3 factorial, and there are 3 choices. So 2 W. Right. Okay. My bad. Sorry. Uh, 8 factorial divided by 3 factorial times by 3. This is 20,160. Now, a team of 6 people is to be chosen from 5 swimmers, 7 athletes, 4 cyclists. So let's do that. Swimmers are 5, athletes are 7, cyclists are 4. There must be at least one from each activity, and there must be more athletes than cyclists. At least one, and more athletes than cyclists. Find the number of different ways this team can be chosen. Right, okay. So first off, let's make different possibilities, and then we can discard which one of them we don't need. So first, let's make different possibilities for that. So you have swimmers, you have athletes, you have cyclists. So what you can have, start off with 1, 1, 4. Wait, sorry, how many do we have? 6 people, right? So we can start with 1, 1, 4. This covers the at least part. So 1, 2, 3, 1, 3, 2, 1, 4, 1, 2, 1, 3, 2, 2, 2, 2, 3, 1. And now we increase the swimmers to 3, 3, 1, 2, 3, 2, 1. And we don't need 3, 3, 3 because that would exceed that. Now, from these, which one of these have more athletes? So more athletes, then this is the one that has more athletes. This is the one. This is the one more athletes. This is the one more athletes. All right. So we have 1, 3, 2. We have 1, 4, 1. We have 2, 3, 1. and 3 to 1. Right, now we need to list there. So 5C1, 7C3, 4. Sorry, let's move this to a side. Right, so 7C1, 4C2, 5C1, 7C4, 4C1, 5C2, 7C3, 4C1, 5C3, 7C2, 4C1. Right, okay. 5C1, sorry, 5C1, 7C3, 4C2. This is 1050. 5C1, 7C4, 4C1. This is 700. 1750. Then we have 5C2, 7C3, 4C1, 1400. Sorry, no. 5C3, 7C2, 4C1, 840. All right, so now we just add them together for the final number. So 1050 plus 700 plus 1400 plus 840. This is 3990. Right, and that's it. All right, so let's move on to the 6-3 variant. All right, so let's see this. Find the number of ways all 9 letters of the word evergreen can be arranged if there are no restrictions. Okay, so first off, let's see this, that there are how many E's? 1, 2, 3, 4. 4 E's and 2 R's. Right, okay, so arrangement with no restriction. So this would be 9 factorial divided by 4 factorial, 2 factorial. So that's 9 factorial divided by 4 factorial divided by 2. This is going to be 7,560. All right. The first letter is R and the last letter is G. So what we are doing over here, that in this 9-letter word, 1, 2, 3, 4, 5, 6, 7, 8, 9, R was one of the ones that would duplicate, 2 R's, so that means that there's no point to worry about the second R, but we do need to worry about 4 E's, right? So basically what we will do over here simply is that R and G have already been selected, so that means we have to select from the 7 remaining letters, and since there are 4 duplicate E's, identical E's, so divided by 4. So basically that's so 7 factorial divided by 4 factorial, that is 210. Now the E's are all together. This is a very simple solution also, like simple working also. So same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9. E's will form a group, and that will become one group itself. So we have 1, 2, 3, 4, 5, 6, 6 units divided by, we had two r's also, so divided by 2 factorial for r's. And we don't have to do worry about the arrangements of e's inside because they're all identical. So we just times by 1. So that would be 6 factorial divided by 2 factorial. This would be 360. Right. 3 letters from the 9 letters of the word evergreen are selected. Selected, not arranged. Find the number of selections which contain no E's and exactly one R. So first off, we need to see what will be the letters left. So evergreen. So no E's, right? So no E's, no E's. Uh, no E's, no E's, no E's. And exactly one R. So that would be just simply, so if R has been selected, so we are selecting from V, G, and N. 3 letters, right? So we need 1, 2, 3. R has already been selected, so it could be V, G, or N that come over here. So this would just be simply 3C2. 3C2, so simply 3 ways. Right, okay. Find the number of selections which contain no E's. All right. Now, over here, we have to take care because R's are identical. So no E's would we have to consider the possibilities in which we have 2 R's, 1 R, and 0 R. So we will do, what if 1 R is selected? We can start with 0 R, sorry. If 0 R is selected, that means you have 1, 2, 3, all the V, G, N, that. So that would be just 3C2. Again, 3 choices do we have. 1 R has been selected, so we already did this one. So that is 3C. Oh, sorry, this is going to be 3C3, my bad. 3C2. And if 2 R's are selected, that means there's only one choice, so 3C1. So the total would be basically just the sum of I equals to 1 to 3 of 3CI, or basically 3C3 plus 3C2 plus 3C1. If you have cases like this, you can basically work out in the calculator. So 3 from 1, 3CX, 3CX, this is 7. Right, okay. And that's it. All right, let's move on to the October-November sessions. All right, so let's see this. Find the number of different ways of arranging all 9 letters of the word pineapple if no vowel A, E, I is next to another vowel. So point to note over here is that there are 1, 2, 3, 4 in quantity. So it's A, E, E, I, O. No, sorry, not O, my bad. Right, so 4 in quantity. And we don't want them next to each other. That means all of them should be in alternate places, or at least not just simply next to each other. So the rest of the letters P, uh, N, P, P, L, and point to notice that you have three P's, two E's, duplicate, identical. So we need to accommodate the vowels in alternate places because we can't keep them together. So for the consonants, you have 1, 2, 3, 4, 5 factorial, but out of them are 3 duplicate. 3 duplicate. Now for the vowels, V, 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 V. For the vowels, you have how many? 6 places. 6P4. But out of those, you have 2 duplicate. You can also write it as 6, 5, 4, 3 because there are 4 vowels, and divided by 2 factorial for these 2 e's. So either way, you are going to get the same answer. So 6p4 divided by 2, this is going to be 180. Now, uh, total ways, right? Total ways we need to combine them. So not add them, but combine them. So total would be 5, 3 times by 6p4 2 factorial. So whatever this is, sorry, this was 180 times by this. So times by 5 factorial divided by 3 factorial. So this is 3600. Right. A certain country has a cricket squad of 16 people consisting of 7 batsmen, 5 bowlers, and 2 all-rounders, 2 wicket-keepers. The manager chooses a team of 11 players out of 16, consisting of 5 batsmen, 4 bowlers, 1 all-rounder, 1 wicket-keeper. Find the number of different teams the manager can choose. Since this has nothing to do with the order, we can have combinations. All right, so first let's write um, if there are no uh, requirements, so you have batsmen 7 total, bowlers 5, all rounders, let's call that AR 2, and wicket keepers you have 2 also. Right, and we need 5 wait, sorry, I forgot. 5 batsmen, 4 bowlers, 1 and 1. All right, so 5 bowlers, sorry, 4 bowlers, 1 and 1. So if there are no other restrictions, so that would be 7C5 times by 5, C4 times by 2, C1 times by 2, C1. So 7C5 times by 5, C4 times by 2, C1 times by 2, C1. That is going to be 420. Right. Find the number of different teams the manager can choose if one particular batsman refuses to be in team when the one particular bowler is in the team. All right. So the possibilities over here. So let's go batsman, bowler. So we can have both of them not in the team, one of them in the team, one of them in the team. So when both of them are not in the team, so that means, sorry, how many? Right. We need 5 batsmen. So instead, we will be selecting from 6 now. 6C5. From 4 bowlers, you would be selecting 4 bowlers. And there's no condition on wicket keepers and all-rounders. Then if the batsman is here, batsman is selected. So 6C4, no, sorry, 6C4, because you still need to select 4 batsmen. The bowler which is not supposed to be over here, so 4C4 times by 2C1 times by 2C1. And if the bowler is in this time, so out of 6, we need 5 because 1 batsman cannot be selected. From if the one bowler has been selected, that means we need 4C3 and 2C1, 2C1. Okay, just to make sure that we have the right ones. So if neither of them are selected, so that means 1 gone. And if batsman is in, 4C4, right? If bowler is in, so that means 1 bowler has been selected. So out of 4, we are selecting 3, 2C1, 2C1. Right, all right. So that would be 6C5 times by 4C4 times by 2C1 times by 2C1. That is going to be, oh, sorry, 4C4, 24. So the first one uh, will be 24. Second one, 6C4, 4C4, 2C1, 60. And the last one, 6C5, 4C3, 96. So 96 plus 60 plus 24, that is 180. Sorry, that's it. Right, and right, okay, all right. Now let's look at the 6-2 variant question. All right, so let's see this. Find the number of ways all 10 letters of the word Copenhagen can be arranged so that the vowels A, E, O are together and the consonants are together. Okay, so first off, A, E, O, I'm thinking there is more than 2 E's, right? So there are 2 E's. So we have A, E, E, O, and the rest are C, P, N, H, G, N. So we have 2 E's, 2 N's. Anything else? No, I think that's good. So the vowels are together and the consonants are together. So basically these will be 2 groups that we will be making. And the groups obviously can rearrange. So 2 factorial for these 2 units. And inside those, we have 4 factorial divided by 2 factorial for 2 E's. And then for the consonants group, we have 6 consonants. And in them, 2 are duplicate, identical. So basically, the 2 factorial, this one can get cancelled. So you have 4 factorial times by 6 factorial divided by 2. So 8,000, 8640. right? The e's are not next to each other, so we can do the same thing we did in the previous question. So if there are no e's, you have A, O, C, P, N, H, G, N. So e's can be over here, 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 and here. So this is the place for e's. Possible places for e's, not, since obviously we just have two e's, and just to make sure that 1, 2, 3, 4, 5, 6, 7, 8, right? So for consonant, for the non-e's, you have 8 choices, 8 factorial for them. 2 are duplicate n's, so divided by 2 factorial. And for these e's, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can do 9 times by 8, because once you choose 9 places are gone, then 8 places are left. Or you can write it like 8 factorial divided by 2 factorial times by 9p2, whichever way you prefer. So 8 factorial times by 9p2 divided by 2. This is this value, 1451520. Right, okay. Oh, I forgot one thing, E's are also duplicate, right? So these are identical E's, so you would have to divide by 2 factorial also. So divided by 2 further, so divided by that, this would be this. So 725760. I think this should be correct. Yeah, right. 4 letters are selected from the 10 letters of the word Copenhagen. Find the number of different selections if the 4 letters must contain the same number of E's and N's with at least one of each. So we have 2 E's, 2 N's, so there are only 2 possibilities over here. So the E's and the N's, either you have 1 of each or you have 2 of each. We are selecting 4, right? So if 1 of each are selected, so out of the rest 6, right? Because total 10, 4 are these possibilities. So 6C, 2, because you just have 2 places now. And for this one, this would be 6C0. So 6C2 plus 6C0, this would be total would be 60. Right, and that's about it. All right, now let's look at the 6-3 variant question. Okay, so let's see this. There are actually 2 questions in this variant, so we'll see them one by one. So a committee of 5 people is chosen from 4 men and 6 women. So men are 4 and women are 6. William is one of those 4 men and Mary is one of those 6 women. Find the number of different committees that can be chosen if William and Mary refuse to be on the committee together. Okay, so this is easy uh, because there's a possibility that neither of them are on the committee. So we can say that we can make different possibilities for William, Mary. So neither of them, one of them, one of them. This is very easy to figure out. There's actually, once you get the hang of it, there's nothing new about this. So 5 people chosen from 4 men. So if neither of them are there, so from 3 men, you can choose, sorry, I forgot. If two, so all people are identical, basically, all, sorry, not identical. So the rest are basically just 8, C, 5. In this case, this is going to be 8C4, and this is going to be 8C4. Straightforward. Because there is no other restriction over here, how many men have to be, how many women have to be. So any possibilities. So 8C5 plus 8C4 times by 2, you get 196. Right. And that's about it. All right. Now let's see the other question from the same variant. All right, so let's see this. So numbers are formed using some or all of the digits of 4, 5, 6, 7, with no digit being used more than once. Show that using exactly 3 of the digits, there are 12 odd numbers that can be formed. Okay, so in 3-digit numbers, you have 1, 2, 3, 1, 2, 3, and there are only 2 numbers which can make these odd. So either it's a 5 or a 7. So since none of these are used again, the rest 3 possibilities for 2 places, 3p2, 3p2. So basically the total would be 2 times by 3p2. So 2 times by 3p2, this would be 12. Find how many odd numbers altogether can be formed. Now, altogether means they could be single digit, double digit, triple digit, 4-digit number. So single digit, double digit number, triple digit number, or 3-digit number, or 4-digit number. So 4, 5, 6, 7. So in single digits, you just have 2 choices because you just have 5 and 7. In double digits, so again, you either have 5 or 7. So that means from the 3 choices over here, 3 choices over here. So 3, 3, 6. So basically, you can do 3p1 times by 2. Triple digit number. Triple digit number means same thing basically what we just did over here. So 3p2 times by 2. 4-digit number. So 1, 2, 3, 4. Again, we have number ending with 5 or a 7. So then we would have just 3 things. 3p3 times by 2. So 3p1 times by 2, sorry. So this is going to be 6, this is going to be 12, this is going to be 12 also. So 12, 12 plus 8, this is going to be 32 total number of ways. Right. Okay. And that's about it. That's all the questions. Hope you learned something. Hopefully in the next video we will cover year 2017.